Now, if we go way back in chemistry history, before we really had any way of doing any kind of elemental analysis, one of the things that chemists were noting is that a lot of the reactive acids tended to contain oxygen. So these would be things like sulfuric acid, H2SO4, nitric acid, HNO3, phosphoric acid, H3PO4, etc. These are what we call oxoacids. Later, it was noted that there are some other reactive acids that do not have oxygen in them. Instead, they have hydrogen and a halide. So we've got a hydrogen chloride, HCl, hydrogen fluoride, hydrogen bromide, hydrogen iodide, all very reactive acids. So Svante Arrhenius, who we spoke about earlier looking at kinetics, he was really the first to notice that there was a link between all of these different acids and it looked like they all contained hydrogen. So he first proposed that it was the hydrogens that were making things acidic. So we had the Arrhenius theory of acids and bases, looking at whether or not something had an H plus in it, or for bases, why, if it had an OH minus in it. However, the Arrhenius theory was not terribly complete, and it had a difficult time describing why a substance like ammonia, NH3, had base properties, since it did not share any characteristics with the other common bases such as sodium hydroxide, potassium hydroxide, lithium hydroxide. All of those original Arrhenius bases all had metals and hydroxides. Ammonia has none of those, but still has the same base properties. So sometime later, a theory was brought about, the Bronsted-Lowry theory. This still supported the Arrhenius theory. However, it expanded its capability of bringing in other compounds that also had acid-base properties. So Bronsted-Lowry acids are now defined as compounds that donate a proton, which is just going to be an H plus, during a reaction. And our Bronsted-Lowry bases are now defined as compounds that would accept a proton during a reaction. So if we look at these definitions really close, we'll notice that they're not specific to that substance's just intrinsic chemical properties or its chemical makeup. We don't care if it has an OH in it or not. We don't care if it has an H in it or not. The key here is that we're looking at its behavior during a reaction. Does it accept a proton or does it donate a proton during a reaction? And that's what's going to determine if it's going to be treated as an acid or a base. So the other implication this has is that it means something, a compound, cannot be strictly defined as either an acid or a base. We can't always say that this is an acid or that this is a base, period. There are several compounds that can behave as either an acid or a base. So let's take a look at an example here. This is just acetic acid, CH3CO2H plus water, and it gives us the acetate ion and H3O plus. So here we see that the acetic acid has lost a proton here. Let me bring up my drawing thing here. So this H is no longer here. Okay, so this has gone to the water, and water has become the hydronium ion. So my acetic acid has donated an H+, which makes it an acid. Water has accepted that H+, which makes water a base. We don't normally think of water as a base, but again, we're just looking at its behavior in the reaction. So water behaves as a base. Now, the other term that we haven't heard about here are the products here. So our acids always have conjugate bases, and bases always have conjugate acids. So your conjugates are always in the products, and they always differ by just a single H+ from their parent compound. So in Bronsted-Lowry theory, we're going to have acids and bases, conjugate bases, and conjugate acids. So again, here we want to say what lost an H, and we see that it was the acetic acid. What gained an H+, and we see that it was the water. So that's why we define water here as a base. Let's go back to the bugaboo of the Arrhenius acid-base theory. and that's ammonia. So ammonia was one of the primary compounds that led Bronsted and Lowry to develop this theory, and they actually developed it independently. They weren't working together, but they came up with the same basic concept around near the same time, so they're given joint credit for it in the history books. But it was really ammonia having its base properties and not fitting into the Arrhenius theory that prompted their new theory. But now with the Bronsted-Lowry theory, we have a way of describing why ammonia has base properties. If we look at what ammonia does in water, we got NH3 and H2O. It takes an H plus away from water and leaves us with NH4 plus and an OH minus. And now if we look at this reaction, we see that water has lost an H plus, and here we would treat water as a base. So now in the last two reactions, we've categorized water as an acid and we've categorized it as a base. It just depends on what it is in the reaction with. So because water can go both ways like that, and it does so fairly easily, we would classify water as being amphiprotic. And that just means that it can either lose or gain a proton and act as an acid or as a base, depending on the conditions. Well, earlier in this earlier slide a couple ago, we introduced this term of a conjugate. We had conjugate acids and conjugate bases. So your conjugate acids and bases are the compounds that have the acid and base properties in the reverse reaction. So if we have what we call weak acids and bases, and we'll talk about those later, we are always going to have an equilibrium situation set up in our acid-base reaction. So if we have an acid and base in the forward reaction, we're also going to have an acid and base in the reverse reaction. So we saw in that reaction a couple slides ago, acetic acid and the acetate ion make up a conjugate pair. In the forward reaction, your acetic acid was acting as the acid. In the reverse reaction, the acetate ion was the conjugate base. So acids have conjugate bases. For the other compound, water, we saw water was acting as a base and becoming H3O+, and that's its conjugate acid. So in the reverse reaction, H3O+ would be acting as the acid, and H2O would become the base on the other side. So if we look at these two compounds, we see that our conjugate pair only differ by that single H+, and that's key. It can only differ by a single H+. So we'll expand on this idea of conjugates a little bit in the next lecture, but that finishes out lecture 12. Some difficult concepts to make sure you read up on, and as always, if you have any questions, please make sure you contact me. Well, welcome to lecture 13 for Chemistry 143. We're going to start off talking about how molecular structure of our acids affects how acidic a particular compound is. And we've got a couple of different acids we're going to look at, or types of acids. The first one is an HX acid, or a halo acid. X is generally used to represent a halogen, so fluorine, chlorine, bromine, iodine type atom there. So if we look at the trends in acidity, what we see is that as we move down group 7, the halo acid becomes stronger. And if we look at the different strengths, HF is the only weak acid of the group there. HCl, HBr, HI are all considered to be strong acids, and of those, HI is the strongest acid if we're in a solution or in a solvent other than water. If any of those are in water, they're all the same strength. They're considered to be strong acids, and again, HF there is considered to be a weak acid. So why is that aqueous solution kind of special? Well, regardless of the number of H+ ions that react, they all react with water very quickly, and you end up with H3O+. So regardless of the strong halo acids there, they all form the exact same acid, H3O+, in solution. So they all have the same strength. So of the halo acids, we have HF as a weak acid, and H combined with any of the other halogens is considered to be a strong acid. Now we also have oxo acids, and we talked about those. So in these oxo acids, things like nitric acid, sulfuric acid, the number of oxygens plays a major role in determining how acidic that compound is going to be. And as the number of oxygens attached to the central atom increases, the acidity increases as well. So let's just take a look at two related compounds here, nitric acid, HNO3, and nitrous acid, HNO2. We see the only difference between them is a single oxygen attached to that central nitrogen. HNO3, nitric acid, is one of our strong acids, and you see there it has a pKa of minus 1.4, and that probably doesn't mean a whole lot to many of you right now. It's all right, we'll get to that point. But the lower that value, the stronger the acid is. And there we see with nitrous acid, HNO2, we consider that to be a weak acid, and that has a pKa of 3.3. So a higher value, and so it's less acidic. And as we see, it's actually a weak acid versus a strong acid like nitric acid. Now, the reason behind the observation of the number of oxygens has really been debated for a lot of years. Different textbooks will put in different reasons, and nobody's really entirely positive on what effect those extra oxygens have. But the observations are all fairly clear. It's just the reasons that are all a little bit muddied there, but all those central atoms are fairly negative. You'll see sulfur in the middle, phosphorus in the middle, nitrogen in the middle, all fairly electronegative atoms. And the greater the number of oxygens that are on that central atom, the greater the number of resonance structures can exist on the ion, and the more acidic the acid tends to be. And the reason, one of the reasons they think that may be, is that these resonance structures, if you remember those when you're doing dot structures, resonance structures stabilize that ion. The more ways that you can distribute a charge on there with resonance stabilizes that ion, and the more stable it is, the more likely it is to exist. Another way that some people look at it is the more oxygen atoms you have on that central atom. Since oxygen is so electronegative, the more pull you have of electron density away from that external oxygen-hydrogen bond, and the easier it is for that oxygen-hydrogen bond to break and give you the H plus that makes it acidic. And if you go into any kind of biochemistry or organic chemistry, you'll run into carboxylic acids, and their stability and their acidity can also be explained by using resonance stabilization of the ion once the hydrogen goes away. Well, we used a couple of terms there that you may not have been familiar with, referring to the acid and base strength. And we very frequently refer to acids and bases as either a strong acid or a weak acid. This is not a very descriptive term, and we want to make sure that we don't have a misconception about what strong or weak really means. Acids and bases both vary in their strength, and when we talk about whether or not an acid is strong or weak, what we're really talking about is how strong of an electrolyte is that acid or base. A strong electrolyte is a compound that breaks up completely in solution and has a lot of charge carriers, ions, in that solution. So a strong electrolyte with acid properties would be considered to be a strong acid. A weak electrolyte, well, actually we'll talk about strong acids here. So our strong acids then ionize completely in solution, and we have no equilibrium set up in that solution. They break apart, and that's all that happens. They don't get back together. Weak acids are acids that are weak electrolytes, and a weak electrolyte is a substance that in solution just breaks apart partially and has an equilibrium situation set up in solution where most of the substance would be associated and only part of it be dissociated, and the associated part and the dissociated part are in equilibrium, coming back together and breaking apart. If you have a weak electrolyte with acid properties, we call that a weak acid. So weak acids will ionize only partially, and as a result we get an equilibrium situation setting up in water. And we'll look at each of these in a little bit more detail. So let's take a look at strong acids. So here's hydrochloric acid, HCl, and it's a gas actually, hydrogen chloride gas. And when we bubble that through water, we get hydrochloric acid. And so HCl and water react, and the H plus comes off of the chlorine. It gets grabbed by the water, forming the hydronium ion, H3O plus, and we get a chloride minus ion floating in there as well. Notice that we do not have the equilibrium symbol in there. We just have that one arrow. It's a 100% reaction is what we consider it to be. It only goes to the product side. So in reality, there is an equilibrium. There's pretty much always an equilibrium for any reaction, but the equilibrium is shifted so far to the right, and the amount of reactant left over is so small that we don't worry about that equilibrium. And so we essentially say that there's no equilibrium that exists with this reaction. We have a complete dissociation or ionization of the HCl, and as a result, with a strong acid, your concentration of the H3O plus ion is going to be the same as your initial acid concentration. So another way of looking at this in terms of our conjugates is to say that we have a very strong acid, and the conjugate base of your strong acid HCl is going to be the Cl minus. And we don't think of the chloride ion as being a base in any way. It really has no base properties, and so the stronger your acid, the weaker its conjugate base, and so your actual strong acids have ineffective conjugate bases. So we don't consider the chloride ion to have any base properties at all. And one of the things you want to make sure that you do understand, or that you know kind of off the top of your head, are the 6 strong acids that we use in general chemistry. So we've got 3 of the halo acids there, HCl, HBr, and HI. And then we've got 3 oxo acids as well, HNO3, H2SO4, and HClO4. So that's perchloric acid there at the end. It's very important to understand when you have a strong acid, so you know if you have an equilibrium situation or not. If an acid is not one of the 6 strong, then you know that it's weak. And if it's weak, we will have an equilibrium situation that we have to deal with. So now let's turn our attention to weak acids. So again, weak acids are substances that are weak electrolytes and have acid properties. And so our weak acids just ionize or dissociate very slightly, and we get an equilibrium situation setting up in our solution. So here we just have a generic acid, HA. It's not any particular one. So HA plus H2O, the HA loses an H plus and becomes H3O plus and an A minus. Your A minus is just the counter ion that comes from the acid. And we see there we have an equilibrium symbol there indicating that that reaction is going back and forth. And since we do have an equilibrium situation setting up there, we can write an equilibrium constant. And since this equilibrium situation is very special, representing the ionization of a weak acid, we give it its own special name, Ka. So Ka just means acid dissociation constant or acid ionization constant. Sometimes you'll hear both names. We still write our equilibrium constants the exact same way. It's still products over reactants. So our products are the A minus and the H3O plus over the undissociated acid HA. And notice what's left out is water. We don't include water, liquid, in an equilibrium constant, or in the expression. It is already factored into that constant. So again, still products over reactants. Let's look at some values here of equilibrium constant values for weak acids. We've got quite a range of Ka values here. At the top there, we've got chlorous acid, HClO2. It's got a Ka of 1.1 times 10 to the minus 2, so not a very small Ka at all, which means that as far as weak acids go, that one is actually fairly strong. It dissociates quite a bit for a weak acid. And then as we go down the chart there, we see down at the very bottom we've got phenol, and that has a Ka of 1.3 times 10 to the minus 10. So that equilibrium lies quite a bit farther to the left on the reactant side, and you have a lot less dissociated phenol there and very little H3O plus produced. So that would a solution of phenol compared to a solution of chlorous acid would be a lot less acidic. All of these solutions are aqueous solutions, and we've seen that an interesting property of water that it can act as either an acid or a base depending on what it's reacting with. As an interesting property of water is also that it can auto-ionize, and it can act as both an acid and a base simultaneously with itself. And so there we see we have two water molecules. They may collide. One of those water molecules is going to take a hydrogen ion away from the other water molecule, and that would give us an H3O plus ion, and the one that had it taken away now forms a hydroxide ion, OH minus. And this is an equilibrium situation, which means we can write an equilibrium constant expression for this reaction as well. So we just write products over reactants. Kc is equal to the hydronium ion, H3O plus, times concentration of the hydroxide ion, OH minus, over our water squared. But of course, we don't include water in our equilibrium constant expressions because their concentrations are constant. So we're going to take those out. And what we end up with is our Kc concentrations. But again, this is a very special type of equilibrium situation, the auto-ionization of water. So it has its own name. We just call it Kw. It's still an equilibrium constant. It's just a very special one. So we have Kw is equal to concentration of H3O plus times concentration of OH minus. When we're dealing with acid and base solutions, this becomes an extremely important equilibrium situation in any aqueous solution. What this means is that the hydronium ion concentration times the hydroxide ion concentration always has to meet the Kw value. And so as one goes up, the other one goes down. But it also means that if I know one, I can find the other. So let's talk about this ionization constant in a little bit more detail here, Kw. So Kw at 25 degrees Celsius has a value of 1 times 10 to the minus 14. Sometimes we may see KWs at other temperatures, and it's just something that you have to you make sure that you keep track of. If you're not given the temperature, you can assume that a solution is at 25 degrees Celsius, and you're going to have a KW of 1 times 10 to the minus 14. But I do know that the book and sometimes the homework problems, they will throw a different temperature at you, and you'll have a different Kw because equilibrium constant values do change with temperature, and the Kw is no exception. Now, in pure water at 25 degrees Celsius, the H3O plus is going to equal the hydroxide ion minus, and those are going to have values of 1 times 10 to the minus 7. In essence, the square root of 1 times 10 to the minus 14. Now, in pure water at any temperature, the concentration relationship there remains the same. The hydroxide will equal the hydronium ion concentration. It'll just have a different value than 1 times 10 to the minus 7 if the Kw is different at that different temperature. Now again, in any aqueous solution, the Kw equilibrium constant value must hold true, okay, which means that your hydronium times hydroxide has to equal the value for Kw. So as the hydronium increases, the hydroxide decreases, and vice versa. So as the hydroxide increases, hydronium will decrease. So we can now determine, or we can use our hydronium and hydroxide ion concentrations to determine if a solution is acidic, basic, or neutral. So if the hydroxide is less than the hydronium here, then the solution is going to be an acidic one. If the hydronium is less than the hydroxide, then the solution is basic. Or if the two ions are equal to each other, then we say that that solution is neutral. So let's take a look at an example here. We want to know what is the hydroxide ion concentration in a solution that has a hydronium ion concentration of 3.2 times 10 to the minus 6. Well, I'm looking for hydroxide and I know the hydronium. I know the relationship between those two is governed by the Kw. We know that Kw is equal to hydronium times hydroxide, and that's equal to 1 times 10 to the minus 14. I plug in the value that I know for my hydronium ion, and I get 1 times 10 to the minus 14 is equal to 3.2 times 10 to the minus 6 times the hydroxide. I solve for the hydroxide and I get 3.1 times 10 to the minus 9. Now we saw with those two concentrations in that problem that concentrations of hydroxide and hydronium in solutions do tend to be pretty small. Now because these values are used so frequently, a more convenient way of expressing either of those concentrations was developed. And for the hydronium concentration, it's called the pH scale. Now pH is actually a unitless value, and it has an equation. It says the pH is equal to the negative log of the hydronium ion concentration, so the negative log of H3O+. So now we have a new way of defining if something is acidic or basic when looking at its pH value, which is a little bit more common way of looking at the acidity or basicity of a solution. So if the hydronium ion is greater than 1 times 10 to the minus 7, then the pH will be less than 7 and the solution is acidic. So anytime you have a pH value that is less than 7, the solution is going to be acidic. And the more it drops below 7, then the more acidic that solution is. If the hydronium ion is less than 1 times 10 to the minus 7, well, that means that the hydroxide would be greater than 1 times 10 to the minus 7, and the pH should be greater than 7. And so that solution now is basic. So if you have a pH greater than 7, then the solution is basic. And the higher the pH, then the more basic that solution is. If you have a situation where the hydronium ion is equal to 1 times 10 to the minus 7, then the pH is going to be equal to 7, and that solution is neutral. And again, these values are strictly for an aqueous solution at 25 degrees Celsius. If that temperature changes and the Kw changes, then the pH values for acidic, basic, and neutral will also change. So again, one of the more important things you've got to remember as you're comparing pH values, notice that as a pH value increases, the solution becomes more basic, and as that pH decreases, it becomes more acidic. One of the more common misconceptions is thinking that something with a pH of 2 is more acidic than something with a pH of 1, when in fact it's just the opposite. Okay, the lower that pH value, the more acidic something is. Now we have the pH scale. We also have a pOH scale, which is really no different in terms of whether it's pH or pOH, just a matter of what we're taking our calculation, or what concentration or what species we're taking our P calculation of. So for pOH, we just do the calculation pretty much the same, but rather than the hydronium ion, we use the hydroxide ion. So pOH is equal to negative log of the OH minus. And a lot of times the pOH scale will be used for solutions that are more commonly basic as opposed to solutions that are more commonly acidic, or if we just don't know. You don't see pOH as often as you see pH, but occasionally it does show up. What we eventually can derive, if we want, is that the pH value of a solution plus its pOH value is going to equal 14. The 14 comes from the 10 to the minus 14 for that kW. Here's another example that will work out in class, and you can certainly try it before class. The pH of a rainwater sample is 4.82. We want to calculate the H plus and the OH minus concentrations in this sample. And so if we have the pH and we want the H plus concentration, we just need the inverse function, and we can say that the concentration of H plus is equal to 10 to the minus pH. So you can give that a shot before coming to class, but we'll work this one out in class. And in the previous lecture, we had talked about the acid ionization constant, Ka, and what we want to learn today is how do we use that value, Ka. Well, it is an equilibrium constant, as we learned, and as we see, most Kas are fairly small. The larger ones tend to be in the 10 to the minus 2, 10 to the minus 3 range, while many of them are in the 10 to the minus 6, 10 to the minus 7, 10 to the minus 8 range. So, like we do with any equilibrium equation or constant expression, we want to use an icebox in order to find one of our species at equilibrium. And for a Ka type problem, what we're usually looking for is the hydronium concentration, H3O+. And this will tell us what our pH is by plugging that concentration into our pH equation. So let's just take a look at an example here. We have a 0.220 molar solution of benzoic acid, and we want to know what the pH is of that solution. Benzoic acid is a weak acid. It has a Ka of 6.3 times 10 to the minus 5. So we're going to start off using an ice table. So we've got our reaction here. Given the formula for benzoic acid, we put that into water. The benzoic acid loses an H+, creating the benzoate ion there and the H3O+. And we don't need to know the formulas, we don't need to know the names in order to do this problem. But let's set up our icebox. So we've got our acid there, we've got the ionized acid and the hydronium ion there. So initially I have 0.220 molar of the acid, none of the ion, none of the hydronium. And so I'm going to lose some of my acid, minus X, and some of that gets turned into the benzoate ion and the hydronium ion, so I get plus X and plus X for those. And so my equilibrium concentrations are just the sum of the IC boxes, and so we have 0.220 minus X for the benzoic acid, X for the benzoate, and X for the hydronium. So our Ka equation we get just directly from our reaction up there. It's products over reactants. So concentration of H3O+ times the concentration of the benzoate ion with negative charge over the benzoic acid. So those have been abbreviated down there in the Ka equation. If your name is Ben, I apologize. It was just easy to put that in there. So we know our equilibrium concentrations of all those species. We don't know the values, but we do have them in terms of a variable. So our benzoate ion is X, our hydronium ion is X, and our benzoic acid is 0.220 minus X. That's equal to 6.3 times 10 to the minus 5. Whoop, that bottom part shouldn't show up yet. So we've got X times X over 0.220 minus X is equal to 6.3 times 10 to the minus 5. So we see that our Ka is very small, so we're going to assume that the X that we're going to get is going to be much smaller than 0.220. And so I can ignore that X that's in the denominator, and that gives me X squared over 0.220 is equal to 6.3 times 10 to the minus 5. And when I solve for X, I get 3.7 times 10 to the minus 3. And if we look at our ice box, we see that X happens to be equal to the concentration of our hydronium ion H3O+. So I'm looking for the pH according to the problem, so I take the negative log of my hydronium ion that I just found, and I get a pH of 2.43. Now we want to go back and check our assumption. Is our value for X that we found truly smaller than 0.220? Well, I take the value for X, divide that by the 0.220 that I would have subtracted it from, multiply it by 100%, and I get 1.6%. So in essence, I introduced a 1.6% error into my answer by ignoring that bottom X, and that's fine. As long as it's less than 5%, that's an okay answer. So we've talked a lot about acids, and now we're going to turn our attention onto bases. And we study our bases very similar to the way we studied our acids. And with bases, we can do something very similar to what we did with our acids, which is to look at strong and weak. And for our strong bases, we see that we have a complete dissociation there as well to what makes them strong electrolytes with base properties. And so we have NaOH, and that goes to Na plus OH minus. And as you see, once again, we have just that single arrow. We do not have a backwards arrow indicating an equilibrium. That single arrow indicates this reaction is moving just in that one direction. So when we dissolve NaOH into water, we do not get an equilibrium situation setting up, and all of that NaOH dissociates into sodium ions and hydroxide ions. Now, just like we did with our strong acids had ineffective conjugate bases. We can do the same thing with our strong bases. Our counter ion, or our conjugate acid for NaOH would be the sodium ion, and that is ineffective as an acid. It does not neutralize with OH minus. It does not re-react and reform sodium hydroxide, and so your strong bases have ineffective conjugate acids. Now the strong acids are the group 1A hydroxides, so sodium hydroxide, lithium hydroxide, potassium hydroxide, and many of the group 2A hydroxides, not necessarily all of them, but most of them. Finding the pH of a strong base is done very similar to how we find it for a strong acid, simply because we have that 100% dissociation there. So once we know the concentration of the base, we know the concentration of the hydroxide ion. So if we want to know what's the hydroxide ion concentration for a 0.050 molar sodium hydroxide solution, well, the answer there is 0.050 molar. We have sodium hydroxide going completely to sodium ions and hydroxide ions. So strong bases, strong acids are always easy to deal with. Weak bases, on the other hand, just like weak acids, have an equilibrium situation that sets up. But rather than having an H plus being donated to the water, what's happening here is that our H plus ions are getting taken away from water by the base. So if we look at ammonia, ammonia plus water goes to NH4 plus OH minus. And we see that we have an equilibrium situation setting up there. So the NH3 is taking the H plus away from water, causing the ammonium ion and hydroxide to form, and hydroxide can take the H plus away from the NH4 plus, giving us water and ammonia back. And weak bases also have an equilibrium constant. We call it Kb because it does indicate that a base is taking H plus away from water, so it's a very special type of reaction, just like the Ka. So we have that base ionization constant. It's still products over reactants. It is still an equilibrium constant expression. The only reason it has its own little letter there is to indicate that it's a special situation. So we have concentration of OH times concentration of NH4 plus over concentration of NH3. Well, here's an example looking for the pH of 0.55 molar solution of ammonia NH3. It's got a Kb of 1.8 times 10 to the minus 5. So this is an example that we will work out in class. If you want to give it a try on your own, I certainly encourage that before class, and hopefully you can get that. Now, if we look at how strong a conjugate is in terms of its acid and base strength, we can look at tables of Ka and Kb values. We would notice that the Kas and Kbs for our weak acids and weak bases are fairly small, 10 to the minus 3, 10 to the minus 4, 10 to the minus 5, etc. Those K values always favor the reactants. But the larger that K value, the stronger that acid or base is going to be. So, and the weaker the parent acid, the stronger the conjugate base is going to be, or vice versa. The stronger the acid, the weaker the conjugate base is going to be. And we can say the same thing for bases as well. We can look at this relationship in a nice graphic from your book. So here we see a nice graphic from your book. We see as the acid strength goes up here on the left-hand side, the base strength goes down, and so we go from strong to weak to neutral as we go up that chart, and vice versa. As that base strength increases as we go down, the acid strength is going to be decreasing as you go down. So this gives us a relationship between our acids and bases and the conjugates. Now, if we want to relate the Ka and the Kb of a conjugate pair, we see that as one goes up, the other goes down. And we can actually form a quantitative relationship between these two things. And what we see is that the product of an acid's Ka and its conjugate base's Kb is going to be equal to Kw, or vice versa. A base's Kb and its conjugate acid's Ka, that product is going to be equal to Kw, and it looks like this. So Ka times Kb of a conjugate pair is equal to Kw. The Ka and Kb must be for a conjugate pair. It can't just be for any acid or base. It must be for a conjugate pair. But this concept becomes very important when we're looking at calculating some of the acid-base properties of salts, especially if we want to find something like a pH. Now we can also compare the acidity or basicity of a couple of different acids or bases, and we can just look at the p-values of the constants. So if I want to compare two acids, I can look at their pKa's, which is just the negative log of the Ka, or I can, if I have two bases, I can compare their pKb's. The lower the pKa, the stronger an acid is, very similar to pH. And the lower the pKb, the stronger the base is. And that's a little opposite from what we normally think of with pH. But because we're using the Kb, the lower that pKb, the stronger the base is going to be. So we just have to remember the lower the value is, the p-value, the stronger the acid or base is for that particular substance. Or if you're looking at a set of them, the lower the pK values, the stronger the acid or base is going to be. If we happen to have a conjugate pair, we can look at the pKa and the pKb of that conjugate pair, and those two values will add up to 14 for a conjugate pair, just like the Ka times the Kb is equal to 10 to the minus 14. This is why the pKa plus the pKb is equal to 14. Well, let's take a look at a particular set of acids here, polyprotic acids. And we're looking at polyprotic dissociation. And there are quite a few acids that, in fact, can lose more than a single H plus when in solution. So we call them polyprotic. More than one proton, or H plus, can come off. And one of the better examples we have is phosphoric acid, H3PO4. Now, if we just write the dissociation for phosphoric acid, we could write it in one step. Phosphoric acid goes to 3 H pluses, and the phosphate ion there, PO4, 3 minus. However, the dissociation of these H pluses, or the ionization, does not happen in a single step. It happens as a series of equilibria. And as we look at the equilibrium constant values, we'll see that each hydrogen ion is harder to take off than the previous one. So here's our first equilibrium constant here. This would be called also a Ka1 to indicate that's a Ka for the first hydrogen, and we're looking at 7.5 times 10 to the minus 3. Second hydrogen, so this could also be called Ka2, 6.2 times 10 to the minus 8, and then of course this third hydrogen, extremely difficult to take off, and that would be Ka3, 4.2 times 10 to the minus 13. So you can see we have a factor of about 100,000 less for each step trying to take that next hydrogen off that acid. So that has some ramifications when we're dealing with polyprotic acids, and if we're looking for the pH of a polyprotic acid. So they can be a bit of a challenge when we're looking at the various concentrations, because they are capable of donating more than a single hydrogen ion, and we see that each of these hydrogens has its own Ka value for it to come off. Now, if we're trying to determine the pH of a polyprotic acid, generally the only one we really need to worry about is that first ionization. We saw that the ionization constant for that second and possibly third hydrogen ion is very much weaker than that first one, and as a result the first ionization provides pretty much all of the H pluses or H3O pluses in solution, and a lot of times that's all we need to consider for that pH, and we'll take a look at an example here in a little while. Now, if we happen to have a polybasic base where it can absorb more than 1 H plus, this is also generally true. So here are just some polyprotic acids here, and we see if they have more than 1 Ka there's generally a very large difference between the Kas. One of the exceptions to this, however, is citric acid. I noticed we've got 7.4 times 10 to the minus 4 for Ka1 and 1.7 times 10 to the minus 5 for Ka2. So not nearly as large a difference as some acids. It would be interesting to do a calculation there and see how much that second ionization actually produces, how much H3O plus it produces. So what we mentioned before is when we have some of that weak acid or a weak base and we add a substantial amount of its conjugate, we have something that is called a buffer solution. Now, what makes buffer solutions so special? Well, they have both an acid and a base present in that solution, and they don't neutralize each other because they're conjugates, and that gives these solutions the ability to resist changes in pH even when small amounts of strong acid or strong base are added. If you're looking at biological systems, buffer solutions become very important. Our bodies have, I think, 3 different buffer systems present in our bloodstream to prevent changes in our blood pH. Our bodies are very sensitive to changes in blood pH, and we do have some strong acids present in our body, particularly in our stomach. So our buffer systems keep us alive. Now, let's just go back to a solution of acetic acid and acetate ion. So this is the solution we just worked with. We have an equilibrium in there. We have acetic acid plus water going to acetate ion plus hydronium in there. Now let's imagine that we have a solution of all of that in equilibrium. And let's see what would happen if we were to add hydronium ion, so some extra hydronium ion to this reaction. It's going to want to react with the base. Well, the strongest base present in that solution is in fact the acetate ion. So the strong acid's going to react with the strongest base it can find in there, and that's going to be acetate, and it's going to do so in a 100% reaction. So it's going to continue until the acid is completely used up. So this would be the reaction here. So we have acetate ion plus hydronium coming from added acid, and that's going to make more acetic acid and water. So at this point the solution is out of equilibrium because we've reduced the amount of acetate ion and increase the amount of acetic acid. So the solution wants to get back to equilibrium, and so the equilibrium is going to restore itself by returning some of the newly made acetic acid from the reaction with the hydronium back into acetate ion and recreating some of the acetate ion and a little bit more hydronium ion as well. Now, a similar situation would have been caused by the addition of some strong base, but the strong base instead would have reacted with the acetic acid and created more acetate ion, and all of your shifts just would have occurred in the opposite direction. So the addition of hydronium ion caused that equilibrium to be shifted over to the left towards the reactant side, and the reaction is going to have to move back to the right to restore equilibrium. If we added strong base, that would have used up some of the acid, and that would have moved the reaction towards the product side and thrown it out of equilibrium, and so the reaction would have to shifted back to the left to restore equilibrium. Well, here's an example that we're going to work out in class, but what we want to do is calculate the pH of a 1 liter buffer solution that has 1 molar acetic acid, HAC, and 1 molar acetate ion. And there's the Ka of the acetic acid. So give that one a shot on your own. We will work it out in class. Now, anytime we're dealing with buffer solutions, you'll notice that we have something, plus x in the numerator, something minus x in the denominator, and we always seem to be ignoring our x, which is a very, very common situation. It's generally what happens when we're doing these types of calculations. So we have something that's called the Henderson-Hasselbalch that generally works very well. However, we always have to be very careful about the ignoring of x. So the Henderson-Hasselbalch equation is based on the ignoring of x. But if we have very dilute solutions and those initial concentrations are really low, then a lot of times you can't ignore the x, and the Henderson-Hasselbalch equation will fail. For our purposes, it should work fine. But here's the Henderson-Hasselbalch equation here. We have pH is equal to the pKa of the acid plus the log of the conjugate base over the acid concentrations. So what we see really what this reaction or this equation tells us is that the pH of a buffer solution is going to be controlled by the strength of the acid, that's from the pKa, and the relative amounts of conjugate base and acid. And one of the nice things when we look at this equation, we see we have conjugate base over acid. If we are writing our reaction as an acid ionization type reaction, then our log term is still products over reactants, base over acid. Your conjugate base is in the products, and your original acid is always in the reactants. So we still have products over reactants, so it gives us just an easy way to remember of what goes on top and what goes on the bottom. Let's take a look at an example of how we use the Henderson-Hasselbalch equation. Here we want to know what the pH is of a buffer solution made with 0.18 molar sodium bicarbonate and 0.170 molar sodium carbonate, Na2CO3. And we're given the Ka of bicarbonate ion there at 4.8 times 10 to the minus 11. So if we set up our equation as a acid dissociation equation, we have our bicarbonate ion, HCO3 minus, is our acid reacting with water. It's forming hydronium and its conjugate base, carbonate ion, CO3 2 minus. And so we have our acid and our conjugate base both present in solution. They're in different concentrations, and that's okay. So we have a pKa of negative log of the Ka value, so the negative log of 4.8 times 10 to the minus 11. That gives us a value of 10.32. We take that value and plug it into our Henderson-Hasselbalch equation, which is pH is equal to pKa plus log of conjugate base, which is carbonate, over the acid, which is the bicarbonate. So the pH is equal to 10.32 that we calculated for the pKa, plus the log of 0.17, that's the concentration of the carbonate ion, over 0.18, the concentrate of the bicarbonate ion. When you plug that in your calculator, you get an answer of 10.30. So you will get a basic pH from this particular buffer solution. Now, when you're making a buffer solution for whatever reason, and this may be something that some of you may have to do in some sort of biology class or in a research lab or whatever your future has in store for you, but there's a lot of solutions that can have measurable concentrations of a conjugate pair but not be effective as a buffer. For example, if you just add some strong base to a weak acid, eventually you will have some of a conjugate base and an acid, but you may not have enough of that pair to be effective as a buffer. Ideally, in order for a buffer to be effective at all, that base to acid ratio needs to be in the range of 0.1 to 10 to be an effective buffer. And so what that really does as far as the pH range is we can take a look at the acid part of the buffer, and if you take the pKa of that acid, if you have a pH somewhere in the range of plus or minus 1 of the Ka, then that solution can be an effective buffer. If you make it outside of that range, it will not be an effective buffer, or as you're adding acid or base, if you move the pH of that solution out of that range, it will stop being an effective buffer. So buffers are most effective. They can absorb the most amount of acid or base when they have higher concentrations of conjugate pair acid and base in that solution. The lower the concentrations are, the easier it is to change their concentrations and move that effective pH, or move the pH out of the effective pH range. Now, one thing that the Henderson-Hasselbalch equation does is it gives us the ability to calculate how to make buffer solutions with a very specific pH. And it also gives us a way to verify that we have our solutions within that pH range to make an effective buffer. So let's take a look at an example, and we'll just go ahead and work this one out here. We want to know what ratio of sodium acetate to acetic acid is needed to make a buffer solution with a pH of 5. And we know that the Ka of acetic acid is 1.8 times 10 to the minus 5. So we want to set up our reaction. Again, we set it up as an acid ionization reaction. So we have the acid reacting with water going to H3O plus the acetate ion. We set up our Henderson-Hasselbalch equation. We know that pH is equal to the pKa plus the log of the conjugate base over the acid. Again, that's products over reactants. So let's see what we know. We know we want the pH to be 5.0. We take the pKa or the P of the Ka, and we get a value of 4.74. What we don't know is what's the concentration of conjugate base and acid. Or more specifically, really what we want is what's the ratio of base to acid that we need, because that's really all we need is what is that ratio. And when we solve for that ratio of conjugate base to the acid, what we get is a value of 1.8. This means that any molar ratio of 1.8 will give us a pH of 5.0. So ideally, for a solution that we want to be able to absorb large amounts of acid or base, we want those concentrations of conjugate base and acid to be fairly high. If we just need a little bit, then the concentrations can be a little bit lower, but they have to be at that ratio of 1.8 for their concentrations, and that will still give us a value of 5.0 for the pH. Well, let's change our focus now in these applications of acid and base chemistry here. Now we want to look at titrations. And you may have looked at titrations earlier in the year in Chem 141. We're going to look at them a little bit differently. So a little bit of review, however. So titration is a practice of determining a concentration of one substance by reacting it in a very controlled way with another. And so we can control the addition of one of our reactants so that we can measure its volume. This is a very common method used with acids and bases. However, there's lots of different titrations that you can do. You can use oxidation reduction titrations. You can do metal complexation titrations. So a lot of different things you might encounter as you might have to take future chemistry classes. Now, when we do acid and base titrations, there is a very common misconception that we have to make sure that we don't we get out of our minds. We keep that just keep that out of our minds, and that is that the pH at the end point of that titration is always 7. This is simply not true. The only times that this is true is if you are titrating strong acids and strong bases. If either your acid or your base is weak, then your pH will be something other than 7. And we'll see examples of that in lectures to come. Let's first look at the titration of a strong acid and strong base. This is the simplest type of titration to deal with because the reaction goes 100% upon addition. So once that reaction is done, there's no equilibrium to be considered because we know that when we react a strong acid and a strong base, we get a salt and water. And the salt is made up of the conjugates of the strong acid and the strong base, and they have no acid-base properties, so we don't have to worry about equilibrium shifting from the products back to the reactants. So that makes this type of problem much easier to deal with. Now, when we do this type of titration, we really like to work the reaction from the standpoint of moles, or more often what we're going to do in class is we'll work it from the standpoint of millimoles. And all a millimole is 1,000th of a mole. We know that if we take liters times concentration, we get moles. If we take milliliters times concentration, we get millimoles. And since our volumes are generally in milliliters, working in millimoles is usually a little bit easier to do. Now, once we've done the reaction in terms of moles, we can calculate brand new concentrations using the new volume. Since we're going to add volumes of either acid or base, we have to keep track of the volumes, but we can recalculate the concentrations after the reaction with that brand new volume. If you are titrating an acid with a strong base, you're going to see that that pH rises slowly until it nears the equivalence point where the moles of acid is equal to the moles of base. As we start getting closer and closer to that equivalence point, that pH can begin to rise extremely rapidly. So again, at the equivalence point, the moles of acid is equal to the moles of base, and for a strong acid and strong base, we know that the pH will equal 7 at that equivalence point. Again, this is the only time that that's going to happen, is when you have a strong acid and strong base. And here's just a graph of what we would get if we were to do a very slow plot of pH versus the volume of sodium hydroxide added. Here we had no base added, and we had a pH somewhere in the lower 3s. We can see that the pH rose fairly quickly initially, and then as we started to build up the amount of acetate ion, we've created a buffer solution in our titration solution. So the pH change starts to level out somewhat. Here at exactly the halfway point, we've got where the moles of the acetic acid is equal to the moles of the acetate ion. And so at that point, the hydroxide or the hydronium ion concentration is equal to the Ka, and the pH is equal to the pKa. So again, that happens at the halfway point towards equivalence. And then as we go a little farther, we reach our equivalence point here, and we can see that we've got a pH just under 9. And then the pH begins to rise rapidly again until we've just got an abundance of hydroxide ion in the solution, and my pH rises very slowly after that. Talking about weaks with strongs, and we've looked at titration of a weak acid with a strong base, and now we're going to look at a weak base with a strong acid. The situation that we have here is very similar to what we had when we were working with a weak acid and a strong base. The only real difference is that the pH starts at a high pH, since now we're starting with a weak base. And then as we add that strong acid, we reduce the amount of weak base and increase the amount of conjugate weak acid, and as a result the pH goes down since the solution becomes more acidic. And just like we did with weak acid and strong base, for a weak base and strong acid we use 2 ice boxes before the equivalents. First we take a look at that 100% reaction of the strong acid reacting with the weak base, figure out how much weak base we have left, how much of its conjugate we've made, and before the equivalents we can use Henderson-Hasselbalch to find the new pH. Now when you're looking for the new pH, you can use either the Kb or the Ka and the Henderson-Hasselbalch equation to calculate that pH. If you're going to use the Kb of the weak base, you need to make sure that you adjust your Henderson-Hasselbalch equation appropriately. Or if you're going to use Ka, you'll use the Ka of the conjugate acid and work out your concentrations of the acid and the weak base in your Henderson-Hasselbalch, and you'll still get the same answer regardless of which of those you choose. Just you have to be aware that Ka and Kb in the Henderson-Hasselbalch equation use a slightly different version of that equation. Now at the equivalence point, the pH is going to be controlled by the concentration of conjugate acid, because at equivalence point you'll have no more weak base left, you'll have no more strong acid left, and the only thing that you'll have present in solution is that conjugate acid, and so you'll need to calculate its concentration, take a look at its Ka, find that concentration of hydronium ion, and find the pH. At the equivalence point, because all you have left is that conjugate weak acid, the pH for that solution will in fact be acidic. Now once you've added strong acid past the equivalence point, the pH is going to be dominated by the additional strong acid. You're not going to have to take into account the concentration of weak acid at that point. That strong acid is going to determine what the pH is going to be. And here we have a graph of what that would look like. So here we see where we have a basic pH at the start, up in the 10 to 11 range, or 10 to 12 range there. We do go through a half equivalence point here, or a half titration point if you want to think of it that way, where the original weak base concentration and the conjugate acid concentration is equal to itself. At that point the pH is equal to the pKa, and in this case 9.25. And then here we see at the equivalence point all we would have left in solution is that ammonium cation, NH4+, that is a weak acid, and as a result what you're going to have at equivalence point is an acidic pH. Now occasionally we do titrate polyprotic acids. One of the more common is phosphoric acid. Sometimes we'll even titrate sulfuric acid. That's a little bit more complicated to titrate, since both of those hydrogens are fairly strong. The first one is definitely strong. The second one is technically weak. However, it's definitely on the strong side of your weak H pluses for those polyprotic acids. But regardless of what you're doing, anytime you're titrating polyprotic acids, your titrations will give you multiple equivalence points, and we see in the graph there where we have 2 equivalence points. You may notice that that first one, which happens at a relatively low pH compared to the second one, it's not as well defined as what we've seen in the past. And this is just because you've got other reactions taking place. You'll notice that rise in pH isn't quite as dramatic as what we've seen for a monoprotic acid. And then once that first titration is finished, it goes back into another buffer region just right around this place here, and then we hit a second equivalence point where the pH goes shooting up once again at a higher pH, and if we had a third H plus that needed to come off, it would be at a higher pH even still. And this is because the Ka is decreasing. It's requiring more and more H plus to take that off. Now, anytime we're doing a titration, and you've seen this because you've done titrations before, we use something that is called an indicator, and an indicator tells us when we are at an endpoint for that particular titration. Now, the indicators themselves are in fact weak acids or even weak bases, and they tend to be very highly colored at certain pHs. Some are highly colored regardless of what the pH is, but there are certain pHs where they will change their coloring. And so at some given pH, depending on the indicator, the acid or base form of the indicator will dominate the solution, and it will give the indicator a very characteristic color. And as that pH changes during a titration, at some point the form of that indicator is going to change from either its acidic or a basic form. And when it does that, you do get a dramatic color change. And here we see the very stereotypical acid-base indicator there. We very frequently use phenolphthalein as an acid-base indicator, and one of the reasons is because it changes pH fairly close to where the pH of the titration reaches its equivalence point. But the other reason we use it is because it does have a very dramatic color change from colorless at acidic pHs to a very bright pink at the more basic pHs. And here we see at these more acidic pHs, the solution is colorless right at your end point for the titration, just a very faint pink. And if you happen to go past that point, when you start getting very basic into the higher pHs, the solution is a very vivid pink. And so not only does it tell you the color indicate where that equivalence point is, it can also tell you if you go too far, because you get that very vivid pink color there. When you're doing a titration, we'll see in a graph here in just a moment, that indicators can change their colors at a very wide variety of pHs. So it's very important to choose an indicator that changes its color close to a pH close to your equivalence point for your titration. And of course, depending on what you're titrating, your pHs could change at a lot of different areas. Now we'll notice here for phenolphthalein, it does tend to change right around a pH between 8 and 9 for the equivalence point. However, you'll notice because of this this rapid rise in the titration curve, that there's a very small volume change that takes place in this region in here. And so there may be just a small amount of air introduced into the volume, but it's so small that we don't really worry about it. So we go through a very wide range of pH change in going from the acidic form to the basic form, but we do it in a very small volume. So that allows us to use this indicator, even though it changes at a pH between 8 and 9, and even if we're doing a strong acid, strong base, which is at equivalence point at a pH of 7, we notice that the volume between pH of 7 and a pH of 9 for that indicator is has a very small difference. Let's take a look at some of the different indicators that we use. We see here with crystal violet, we've got a pH or two different color changes. We can go from yellow to green at a very acidic pH, and we can go from green to blue, which can be very difficult to see at, again, a very low pH, around 1.5. But we see a variety of different pH ranges here. Bromcresol green is very common. Bromthymol blue is very common as well for acid-base titrations. We frequently use phenolphthalein, and we notice it goes from that, whoops, wrong one. It goes from clear here to this bright pink here, and we have that transition here right in that 8 to 9 pH range. And but again, because that color change happens so quickly with such a small
difference in volume. We can use that for a pH change that is expected around 7. Other indicators, we see thymol blue up here, actually has 2 pH ranges depending on where it's at, and again, it's just because of the nature of the indicator itself. Alizarin has 2 different pH changes, one in the acidic, one in the very basic. So for our purposes that we do in lab, we always change those, or we choose those indicators for you. But as you start moving up in the chemistry world, you may find that you need to choose your own indicator, and you would just go to a graph like this and see what would work best for your purposes.
Well, let's shift gears a little bit and look at Lewis acid-base theory. So this is very different from Bronsted-Lowry theory and much different than Arrhenius theory. So the Bronsted-Lowry theory worked really well for describing how we had protons moving back and forth during a reaction, but there were still some things that gave us acidic solutions or basic solutions that had no protons moving back and forth at all. So an even more general theory was devised to show how the sharing of electron pairs can give us an acidic or basic situation. So it came up with the Lewis acid-base theory, and this is the same Lewis that created Lewis dot diagrams. So Lewis acid is going to be a substance that accepts a pair of electrons in order to form a new bond. And a Lewis base is a substance that donates a pair of electrons to form a new bond. One of the things we've got to be careful here is we're used to thinking of an acid as something that donates and a base as something that accepts. When we're talking about the electron pairs here, it's just the opposite. So the Lewis acid is accepting a pair of electrons, and the Lewis base is donating the pair of electrons to form that bond. Now, once we have a Lewis acid and base react, we have what is called an adduct, a Lewis acid-base adduct. Let's look at this concept of adducts. So acid-base labels still apply, and so H+ we consider to be an acid, and we would consider water here to be a Lewis base, and that creates the adduct, our hydronium ion, H3O+. Okay, our water acts as a base as it donates that pair of electrons to form that covalent bond with that third H+. Remember, a proton has no electrons, so even though there is a covalent bond forming between that H+ and the oxygen atom in water, it's water's responsibility to donate both electrons to form that bonding pair. And we can do the same thing with H+ and NH3 to form the ammonium cation NH4+. The nitrogen has to donate that lone pair and donates both electrons to form that covalent bond. So since this is a slightly different type of covalent bond where we don't have an electron coming from each atom, but rather both electrons coming from just one atom, we call this a coordinate covalent bond. Now, coordination complexes are things that many metal atoms form with simple Lewis bases such as water or ammonia. So highly charged metal ions often act as Lewis acids. We see NH3 and H2O both have lone pairs in order to form a coordinate covalent bond, and really in order to be a Lewis base you have to have a lone pair of electrons available. So if we take a look at ammonia here, it can form a bond, Lewis acid base bond with copper, and that gives us that deep blue that we've seen before in lab, and we see that that copper can bind actually to 4 different ammonias, and several metals can bind with water. We see lots of different metals down there forming our water complexes, and anytime we dissolve these transition metals, just a salt of them, they immediately form these Lewis acid-base adduct compounds with water, and this is really what gives them that color in water. Most of them form octahedral complexes with 6 waters around them. Some, however, form a tetrahedral and just get 4 waters around them. It just depends on the metal and what's going on. That's not something that we have to worry about. We just have to be aware of how this Lewis acid-base pairing works.